Have you ever had this feeling of accomplishment? You know, this feeling of having done the job and having done it right? Like last Friday, for example, your team has just spent the past 2 days writing tests, only tests for your software. And it's Friday evening, you run the tests, and everything works. All the tests pass, and cherry on the cake, you have this wonderful metric that says 100% test coverage, or code coverage. It means everything has been tested. So you're proud of yourself, proud of the team, and you think that I can go on a weekend safely, happily, and enjoy my weekend. But then you go back to the office on Monday, and you open your email, and you still have this feeling from last Friday where you were proud of yourself, proud of the team, everything was OK. And then you have tons of bug reports, Jira ticket, whatever you use, saying that there are bugs in your software. And then you wonder, what happened? What did I miss? Everything was working fine. So a brief history of tests before we begin. What's the most easy way to test a program? Any idea? No,
traditional way to do tests?
No way, no. Everybody is like, shame. OK, so back then, back in the time, to test a program, you had to do it manually. And I know that people are still doing it manually sometimes. And so you had to basically compile your program, run it, execute it like a few times, test everything, and see if it worked. Well, that worked when the programs were like little functionalities. Doesn't work anymore in big programs. You have a lot of classes, a lot of functions, lines of codes. Some programs have millions, some billions of lines of codes. And so that's, at some point, people starting to find solutions. And they came up with these test frameworks. You have a PyTest for Python, Jest for JavaScript, for example. And they made the bug finding process way easier and faster for you. And they even came up with this new matrix I mentioned earlier, the test coverage. Test coverage means that when you have 100% test coverage, it means that all the lines of your code have been executed at least once by the test. OK? And so the question we're going to answer today is, does 100% of test coverage means 100% of my test is tested? Does it mean 100% of my code is ready for production? And so obviously, if we're here today, and not only for 3 minutes, it's because it's not necessarily the case. So hi, everyone. My name is Olivier. I'm a developer advocate for AWS, and today I'm happy to be here with...
Hi again. My name is Maha. I'm an engineering manager at Elastic. I'm leading a team, the releasing engineering team. We provide guidance and framework to the other teams at Elastic to help them, empower them to produce their reusable artifacts. I worked before that as a DevOps engineer, and I also have a PhD in optimizing performance of multi-tier distributed system. And today, we're going to talk about mutation testing. What does it mean? How can we implement it? And how can we benefit from it? So I'm going to start by answering the first question. What is mutation testing? So mutation testing is a technique that helps us to evaluate the efficiency of our test suite. As Olivier just mentioned earlier, having 100% of code coverage doesn't necessarily mean that we are 100% sure that our code does what it's supposed to do. So basically, the idea from the mutation testing is to measure the efficiency of our test suite beyond number of lines of code being executed by our test suite. Simply put, to not get you worried, mutation testing is test of our test. It's crazy, right? We're going to walk you through all those steps one by one, no worries. Historically speaking, the first time this concept appears actually was by a student named Richard Lipton back in 1971. However, the first implementation was a work of a PhD student at Yale University in 1980. And the idea is to create artificial faults and inject them in our system, and then run our test suite against those faults and see if our test suite is able to detect those artificial faults or not. And by that, the mutation testing is giving us actually a score, we're gonna talk about it, to say how efficient our test suite is, how effective. And this will lead us to the second question, why do we need that? Why do we need mutation testing? As we mentioned, to measure the efficiency of our test suite. And why do we care about that? Because the test suite is our primary source of truth to tell if our code is really doing what it's supposed to do, meeting the standards or not. And of course, it will help us improving our test suite by indicating that there are some test cases are not covered by our test suite. There are some hidden bugs. So that way we'll improve our test suite. And last but not least, the mutation testing will help us to point the time and the root cause of any regression in our test suite. So now the main question is, how we gonna implement this mutation testing? So I will give you the general idea, and then we'll break it down to small chunks. So the general idea that the mutation testing is about creating a modified copy of our program, our code, where we do only one modification at a time, and then we run the test suite, the relevant test suite, against this piece of code, this copy. If the test suite fails, that means our test suite is efficient. Why? Because the test suite was able to detect this modification. On the other hand, if the test suite passes the test succeeded, this means that our test suite is missing something. There are some use cases are not covered by the test suite because it didn't detect the modification and the test passed, knowing that I made modification in the code. It sounds a bit crazy because I'm saying that if the test suite fails, it's good. Yes, it is good, meaning that the test suite is able to detect the modification I have artificially injected in the code. But if it passes, it's not good, meaning that there are cases are hidden and not covered by test suite. So let's break it down to small chunks. I know that's a lot of information here. What I called creating a modified copy of our original program, that's what we call it a mutant. So the mutant, it's a modified copy of our original program where we have only one modification at a time. And our goal, our ultimate goal, is to kill the mutant. Killing the mutant meaning that the test suite will fail. Failing the test suite is good. And in that way, we are killing the mutant. Otherwise, the mutant will survive, and our test suite is weak. Let's have a look at this example of creating a mutant. So here it's a piece of code of Python. And what I'm trying to do here is computing the square root of a number. So I'm checking if the number is smaller than 0, then I will raise an error. Otherwise, I will retain the square root of that number. We are good so far. I will write the unit test of this piece of code. So in my test, I will say I have an assert statement where I say that the square root of the 49 is equal to 7. When I run this test, everything is good. The test will pass, and everything is fine. Great. So now I want to create a mutant out of this piece of code. So remember what I said. I want to inject one modification at a time in my code. What I will do, there is this arithmetic operator, which is if the number is smaller than 0, I will change it to make it smaller or equal to 0. So I made only one modification. And then, so this is a mutant. I created a mutant. Then what I will do, I will run the exact test I just showed you against this modification. What will happen, as you can see, the test will pass. And the result that the mutant survived. And that's correct. Why? Because in my test suite, what I tested, it's only one statement where I check that the square root of 49 is equal to 7. So it has nothing to do with the 0. So the test pass didn't detect any modification. This modification hasn't been detected by my test suite. So this means that I'm missing something in my test suite, which is another case, which is if I add another statement by saying the square root of 0 is equal to 0. Actually, if I rerun the test again, so the test suite will fail because it raised an error, there is a modification has been detected, and the mutant will be killed. The mutant has been killed because I added extra test case to my test suite. So in this case, I managed to improve the quality of my test suite. So I showed you one way to create a mutant by making one arithmetic operator change from smaller to equal. And there are many types that we can use to create a mutant, and Olivier can explain us those types.
Yeah. Are you still following? It's been 10 minutes, and usually that's the moment in the conference where half of you is like, what? And the other half is saying that, the seats are comfortable, not that comfortable to stay here.
There is a surprise that there will be 2 demos.
Yeah, everything will make more sense when we run a bit of a demo because the context is a bit complicated. Anyway, let's talk about the kind of mutations. Maha showed you that she changed at some point less to less or equal to. So we have different types of mutations. The first one, so I brought it down to 3. The first one is value mutations. Means we're going to change values. Like you have a 2 that becomes a 0. You have a small int that becomes a big int. You have true that becomes false, a string that becomes an empty string. So we just change values in the code. Very easy. We do that for every kind of constant or variables you have. Then there is some decision mutations. So we take your code, and we're going to change some small statements like if, else, switch, and, or. So we're going to change this. You have and A and B becomes A or B. So we change these small pieces of code. And then we have these statement mutations. In this one, we're going to change entire pieces of code. You have a functions, we just delete it, or just make it an empty function. And so what, as Maha said, we just make this change, and we run the test on every single piece of code that has a mutant on it. OK? So just to show you a little bit, because I mentioned 3 kinds of mutations. We have arithmetic operators, so plus becomes minus, times becomes divided, modulo becomes times. So we just change in your code, there's a minus, becomes a plus. A times becomes a divided. We have some array declaration mutations. So you have an array, can become an empty array, we add more values to it. And remember, we don't change the test, we change your code. So we take your code and we make thousands of duplicates of it, and in every version of it, we change some of these values. We have some assignment expression, plus equal becomes minus equal. We even have a bit displacement here. Block statement, like we have a function, becomes an empty function, and again, we run the test. If the test passes, it means we haven't tested your function properly. Otherwise, it should fail. We have Boolean, so true becomes false. A equal B can become non-A equal B. And we have a lot of these. We have conditional expressions, equality operator, logical operator, string literals, object literals, optional chaining. And as you can see here, these don't exist in every language. So depending on your language, you will have some mutants. Like optional chaining doesn't exist in every language. And you have many more. There's just 2 more I want to show you. The first one is the method expression, because in some languages, like JavaScript, for example, you have some built-in functions, like start with. And some framework, they know this, and so they will change your code with other functions. So start with, become end with, to uppercase, become to lowercase, and that does it for you. And last but not least, what I hate writing regexp. I know some people love it, but I don't. And I hate even more writing tests for regexp. And so here you can also have mutations for regexp. So regexp becomes another one. And then you run your test, and usually that fails because, come on, regexp. So at this point, what I hope you understood is that when you have your code, we'll create thousands of versions of your code, and every one of them we're going to make one change. So you may think, OK, so I wrote my code, it took me 6 months, and you're asking me to rewrite it again. No. There are tools for that. People came up with tools. And there is no like one tool fits all for every language, so there's a bunch of them for many languages. And these tools are going to create the mutants for you. They're going then to run your test, and they're going to give you what we call a mutation score. If I take it down to like an easy equation, the mutation score is the number of mutants killed divided by the total number of mutants. Kind of what you have for the test. The number of tests that passed divided by the total number of tests. It's actually a bit more complicated like that in real, because you may have some code that just go to infinite loop, or because you have like a while loop that just becomes while true. May have some timeout. So there is a bit more behind these things, but it's basically what a mutation score is. And the goal is to get 100%. So very simple, just to make sure you understood everything. If you have a mutation score of 50%, we had 4 mutants created, so 4 versions of the code. 2 were killed, 2 passed, 50%. What we want is to have 100%, like all the mutants being killed. OK? So hope you understood the theory. Let's see some demo now.
Yes. So we prepared for you 2 demos. The first one in Python. How many of you developed some Python? Great, decent amount. You will enjoy the demo. How many of you developed in JavaScript?
OK, nice.
Great. So you will be happy, I'm telling you. Before I start the demo, I have another question. How many of you write tests? Wow, great. Wow, I love you all. How many of you managed to reach 100% code coverage? Wow, wow, great. OK, let's see if that's enough or not. So you are happy with 100% code coverage? Let's see if that's enough or not. So for the Python demo, I'm going to show you the first. There are different tools. The first one is MutePy. The installation is pretty straightforward. Pipe install MutePy. And you have here the official website, where really you can see how you can install it. It's straightforward, so no big deal. And the main command for that is you run the main script, mute.python. You pass few parameters. The first one is your source code, the target. The second one, because we need it, we need to modify it. The second one is the test, your unit test or your PyTest. And then a few other parameters like -m to show you the mutants have been created for that test. And report HTML version. You can, of course, choose if you want the report to be in JSON format, whatever. OK, let's go to my IDE, which is the PyCharm. So what I have implemented, it's calculator. Do you see well, or you want me to increase the font size? People in the back? It's good? All right, perfect. So it's calculator, simple class, where I implemented different functionalities, the add, subtract, multiply, divide, and so on. And I also implemented some unit tests, okay, to test, for example, the add. There is an assert statement, the subtract, and so on. So I'm going to run the code coverage for that. I'm using the coverage Python library. And it shows, as you can see here, 100% code coverage. OK, that's great. So we think at this moment, everything is perfect and everything is working well. OK, and this is, I know that's a magical moment for every developer when you see 100% code coverage on the screen. Yes, we did it. We are so proud. OK, what I'm going to do now, I'm going to do a manual modification in the code. And then I will run the test against that modification. So I'm going to, for example, do this modification for the multiply. So for the multiply, instead of putting, for example, the multiply, I will change it to, or for example, this one. I will change constant. Let's change, instead of arithmetic operator, I will do something different. So here in the divide, I can change a constant. So it was 0, and I will put 1. And then I will go to my test. And I can run either all of them or just only the one for divide. And let's see what will happen. OK. The test pass. The test pass means that my test suite didn't detect that I made a small modification in the code. So what I want to do, I want to assert another thing in the divide. I will add another statement, actually, which is this statement. Oops. And I will say division by 1 equals to 4. I will run the test again. The test failed, because it detects that there has been modification in my code. OK? So this is the traditional way, just to explain you simply how we do that. But as Olivier said, that there are tools to do that for us. So what I'm going to do, I will put that back, remove it. OK. And I will put my code back to what it was. And let's use the tool. It will do the job for us. So the mute by, I can run it. So here, if you can see, it's exactly the same command, but I'm running it in a Docker, because actually this tool doesn't work in Mac, so I had to run it inside Docker, but in Linux, it works fine. I tried it already. So I'm going to run that, and let's see what will happen. As you can see, so we already know that the code coverage for this code, it was 100%. And running the mutation test using this mute_by tool, it shows that the mutation score is only 64%. And it says that there are 14 mutants have been created, which means 14 modification, 14 copy of my code, where there is 1 modification at each copy, in each copy. 9 of them got killed, which is great. But there are 5 survived. And if you can go back to the whole report, actually, here, it will tell you, so for example, this one is killed. OK, great. This one is killed. Let's look at one survived. The one survived, actually, wow, the multiplication. So in this mutant, what he did, he changed the operator from multiplication to exponential. And run the test against it. Let's look at the test for the multiplication. So in the multiplication, the test of, for multiplication, I'm testing if the multiply 2 by 2 is equal to 4, it's good. But if you change it to exponential, the result is the same. So that's why the test will pass. So even if I change this operator from multiplication to exponential, the test will pass. Nothing changed. So the test didn't detect that there is a change. So if I want to kill that mutant, what I will do, I will add another statement in my test by saying 2 multiplied by 3 equals to 6. The test is good to make sure. OK, the test is good. Let's rerun the mutation. So remember, what I had 5 survived, sorry. So now with this modification, I'm going to kill one of them. rerun it again, and you can see that 4 survived. Let's see and make sure that the multiplication has been killed. It has been killed, which means that I added this hidden use case to my test suite and was able to detect it, and everything is good. So as I showed you that this is the main idea behind using the MutePy or using the mutation test, let me show you the other part, which is the report. The report can be generated by, so this is the code coverage, the HTML file, and here it's the HTML report by using this MutePy. So if you don't like reading it from the terminal, you can just go to the HTML, you export it in HTML or JSON format. And as you can see here, we increase the score of the mutation. So the mutation score has been increased because I killed 1 mutant. So as you can see that the surviving one, there are only 4. And even more details. So here you see all the mutants have been created, the 14. You can go to each of them and read more details about it. And here it tells you what kind or what type. If it's arithmetic, if it's changing a constant, is it removing completely a statement, like if a block, adding a new statement, and so on. So this is the first tool we have seen, the MutePy, and there are other tools for Python. So this is a gift for the people who develop in Python. There are many tools. The second one is Mute. I played with this tool. The installation is straightforward using pipe. However, what I noticed that the number of mutants will be created using this tool is less. Basically, there were 10. However, in the previous one, there were 14. So it depends. But there is something you need to keep in mind. All those tools, actually, there is a configuration file where you can adjust and you say the percentage of mutants you want to create, what kind. Olivier is going to show us that for the JavaScript one. The last tool for Python, which I recommend to use, I haven't played with it. The community there, it's very active. Also, it's a Mutation test and the installation using the Py. However, it's really if you write your test in PyTest, so it's really has a great support for that kind of test. So that's basically for the Python part, and let's move to the JavaScript part.
Yes. OK, especially since there's a lot of people doing JavaScript here. OK, again, as Maha mentioned, there's several tools for every language. So I just chose one for JavaScript, which is one of the most popular ones. But there's plenty that exist, and choose the one that fits the best for you. So the one I'm going to use is called Striker. Very easy to install in PM install Striker CLI, and then you run it, Striker run. So I'll show you a bit what the website looks like. So basically, this is a Striker website. The tabs are open because the internet connection is not so reliable here. And interesting, so I'm using it for JavaScript, but it works for TypeScript too. There's a .NET and a Scala version for Striker. And you can see for every of these languages what Striker supports. Like, for example, I mentioned optional chaining earlier in the slides. JavaScript has optional chaining. Maybe other languages don't have it. So depending on the language, you don't have all the mutator available. So this is what I showed you earlier. There's many others. You have plugins for every test frameworks, or the most popular ones. So I'm going to use Jest in the demo, but it works with Cucumber, Jasmine, Mocha, Karma. And last but not least, you can also integrate these with your CI/CD pipeline very easily. So now, let me show you. So I have 2 demos. The first one is I kind of did the same thing as Maha. So I have a calculator, very easy, which is here. So add, subtract, multiply, divide, modulo, and square root. I know all the edge cases are not even in the code, but this is the demo, remember. So this is my code. This is my test. So for every of these functions, I've written just one test. And if I run my test. So this will run tests with the test coverage. So here, I don't have 100% test coverage as Maha did. So 100% of my functions have been tested, but I only have a percentage of 88.88%. It means not all the lines of my code have been tested. What I want to show you is that you don't need to have 100% test coverage to to run mutation testing. It will only test your test. So if you have a low test coverage, then the mutation test won't be that reliable because they will only test the percentage you have covered in your code. But anyway, and so now let's run some mutation tests. Run Striker. And so what it does a bit the same thing that Maha had before. So I can see that he created some mutants here. So the less than 0 just becomes like an empty statement. The less than 0 can become false. And so you can see the one that survived and the one that failed. So here I have a mutation score of 77.78. And I have a report here that I can go and see. So my report here looks like that. So I have 77.78 mutation score. And if I look at it in my file, I can see all the mutations that have been created. So these are all the mutants that were killed. So I don't really care about this, but basically the A plus B became A minus B. What I want to see is the one that survived and the one that were not covered. So I don't care about the one that are not covered because I know my test coverage is not 100%. Here I have 2. So if I click on it, I see at some point it tried to replace A less than 0 to false. And the other one is like it changed A less than 0 to A less or equal to 0. So let's work on the first one. If I go back in my code, so I know that there is a test missing here. So I'll write a test just to make sure that I check when I do a square root of 0. And now if I run my Striker again, you will see that I should have a better score. So I have a score of 83.33%. And here you can see that I don't have, I only have the false one here. I don't have the less or equal to 0 because I have a test now for that. So I still don't check the error here. So that means I still need a test. Write a test. So I write a test that checks if I do a square root of -1, I get a number should be positive. So it raises the error. And now if I run my test, you can see that I have 100% of mutation score. So I don't have 100% of test coverage, but I can have 100% mutation score because I only test my test. So I only test the amount of code that my test covers. Does that make sense? Good. I want to show you another demo very briefly. So this is a demo that comes with Striker, so you can run it, clone it on GitHub. It's there. It's a simple application. It's like a robo-bar, so you can order things, submit order, view the orders, make new order. So very simple application. It's written in AngularJS, Angular, I think. No, hope so. And so very simple application, but still there is more code on it. So if I go there, you can see it's a kind of a bigger application. If I run the test, it will give me a test coverage. And here you can see in every single file, I have a test coverage of 100%. It means every line of code at some point when running the test have been executed. So I don't know how many in the room are product managers, POs? OK, so next time someone tells you 100% test coverage, you see, everything is tested. Yep, not necessarily. So let's run Striker now. So when I run that, so it will create a lot of mutants. Here you can see it creates 115 mutants. So the code is not that big, but still it's more than what we had before. And now we can see that the mutation score is low for some files. I can go in the report. So the report is a bit bigger. Here you can see like 57.72% of code coverage. And I can go to any component, this one, for example, and see all the mutants that have been created that survived. So I know that I may have 100% test coverage. There's a lot of edge cases in my code that haven't been tested, because when I modify it, the test still pass, which is bad. OK. What are the slides? Are we good? OK, Maha.
All right. I hope that you enjoyed the 2 demos. So we saw 2 demos, one in Python, one in JavaScript, to see how can we implement the mutation testing in our code. And we saw that there are tools will do that for us, so no need to panic. Now the question is, again, like the code coverage and against the mutation score. Having code coverage 100% is great. I'm not saying it's don't try to get it, don't strive to get it. This is good metric. However, it doesn't really tell us how efficient our test suite is. If there are hidden cases, edge cases haven't been tested or covered by our test suite, as you have seen in our demos, right? And that's why we need another complementary metric, what we call it the mutation score. And of course, the higher mutation score you get, the better or more efficient your test suite is. However, keep in mind that some cases, sometimes, you might get 100% code coverage, but you stick at 99% mutation score. And you would like, I want to get 100% mutation score. I will make that happen. Well, you need to accept the fact that there are some exceptional cases where you will not manage to get this 100%. And why is that? Well, it's because that there is a special kind of a mutant, what we call it equivalent mutants. They will prevent us from getting 100% mutation score. What those equivalent mutants? Actually, those they are another kind of mutants, but the change that they produce will not impact the logic of the original code. What does that mean? Let's have an example. So here's the example. I have this code in Python again, where what I try to do, I get an URL, what I want from this code to take this URL and fetch the web page locally. Then I decided, OK, next time I get the same URL, actually, I don't want to go to the server to fetch the web page. What I will do for the first time, I will do some optimization by adding a cache, a dictionary in Python. The key is the URL, and then the value is the web page. So next time I get the same URL, I don't fetch it from the server. I fetch it locally. And this kind of optimization, performance optimization. A mutant, possible mutant for this piece of code is, as we said, like it's not only about operators or changing constant, can be also removing completely a block from the code. So the mutant will be created for this piece of code, removing the whole if statement. And you will imagine the code without the if statement at all. Then running the test against this code, after you remove the if statement, actually the code will still run, and the test will pass. Why? Because you didn't change the logic. Instead of running it, getting this web page from the dictionary, you are getting it, fetching it again from the server. The code might get slower, which is true, because every time you are going to the server, you are not fetching it from the cache. So that's normal. But this is the reason why whatever you do, the mutation score will stay at 99, because of those, what we call them, equivalent mutants. So you need to be aware that those, they do exist. So we saw that mutation testing is great. However, there is nothing perfect in life. And thus, it has limitations. So first of all, I think all of you agree with me that it can be time-consuming, and that because of the large number of mutants can be tested. And that's why we always say that you can't do it manually. You need those tools, and thanks to those tools, where we can use them for free and try to implement the mutation testing. So we don't need really to do these things manually, because it cannot be done, time-consuming and overwhelming for all the developers. And here, actually, this raises a question, which is, how can we implement mutation testing at scale? So you have seen what we showed you in the demos. The first one, we have simple program with a few functionalities. The other JavaScript demo, there was another like medium kind of size of a project. But how can we implement it at scale? And here there is a study by Google, has been done actually last year, where they apply the mutation testing in their code base, which is 2 billion lines of code with 150 million unit tests running on daily basis. So I let you imagine how many mutants can be created for 2 billion lines of code with 150 million tests this week running on daily basis. So it's it's really overwhelming, it's crazy. So you can't do that. So what they propose actually to be able to run mutation testing on this very huge, large-scale code base, they said that we will run mutation testing incrementally, meaning that we run it not in the whole code base, we run it only on the level of the PR, when you have a new code, a new pull request or merge request, whatever you want to call it. So we run it incrementally. They said also we need to limit the number of mutants created per each line of code and per each pull request. As we told you that those tools, you can configure them, you can say the percentage of mutants you want to create, you want to test, and so on. They also say that we want to filter some mutants. For example, there are those equivalent mutants. I don't need to run them because they are not changing really the logic of the program. And they also rely on some heuristical studies of some performance of some mutants based on some developers' opinions. They included a large number of developers to be in that study. So in that way, they were able to implement mutation testing at a scale.
It's something we didn't mention before, but it's very easy. I mean, in Striker, for example, there's a config file. You can say, I want only to do mutants on these files, and I only want to do like Boolean or numerical, arithmetic. So you can choose the kind of mutants you want to create and on which file you want to run them. It's very easy to do.
Yes. Last but not least, of course, you can't apply mutation testing if you don't have the code. It can't be applicable for black box testing. Why is that? Obvious, because you need the original piece of code, the original program, to make a modification on it. So always you need the original code to be able to implement or apply the mutation testing. Well, as takeaway, again, the message is 100% code coverage is great, and you should be proud of yourself, but it's not enough. Sorry, but it's not enough. And that's why we care about the quality more than the quantity of the test. All of us, we know that we can fake this code coverage number by creating bad tests. All of us, we know that. So I can really reach 100% by creating bad tests. So be aware, PM, Scrum Master, that this is, don't tell me that's 100%. All of us, we can do this, trick. So what we care about is the quality rather than the quantity. And as we saw, it can be overwhelming, and that's because all the large number of mutants can be created, and that's why we say that we need automation, of course. Last but not least, it's okay if you don't manage to reach 100% mutation score, because those kind of special equivalent mutants, what we call them equivalent mutants. As we promised, so I know that between Python developers and JavaScript developers, for the rest, who developed in other programming languages, so there are other tools, so don't panic. So for Java, there is really widely used tool, the PyTest for Java developers. It's really widely used everywhere. There is for C and C++, for PHP, and so on for the other programming languages. There is for Golang, if somebody programs in Go as well. Well, here are the list of references we have used to prepare this talk. And you can find our slides here at slides.com/myname. I hope that you really learned something with us, and you know that what we care about to improve the quality of our software is really having a great and efficient test suite. And we achieve that not only by 100% code coverage, by having mutation testing to test our test. So I hope that you're going to really implement that in your team, in your project, or at least share it with your colleague and tell them about it. Thank you very much, everyone. It has been a really great pleasure giving you this talk, and we hope that you enjoyed it. Thank you so much.